Okay, everybody, we are doing Module 4, Lesson 2, and last time we were talking about the electrons in the Bohr model of the atom and how we had energy levels that were broken down into sublevels and into orbitals then. And we were, I was giving you some analogies for what this would look like in terms of like the apartment building. Remember that? And so what we're going to work on today is we're going to work on how to do this in a better and faster way, because we certainly can't go through chemistry describing to people which apartments that electrons live in. So what we're going to do is work on electron configurations. And electron configurations, it's kind of a shorthand way of telling someone where the electrons are in an atom. You're going to be able to tell which energy levels, which sublevels, and how many are in each of those things, okay? So one of our rules as we do this, and I need to see if I can find my pen. There we go. I've got it there. We are going to need to take note of this right here, that electrons tend to take the most stable arrangement possible. This is all about stability. We said in our previous module that protons determine the identity of an atom, but electrons determine behavior. Electrons are all about how the atoms act, and a lot of that has to do with stability. So here is our first rule for electron configurations, okay? We have to follow something called the Offball principle, and it says that electrons will occupy the orbitals of the lowest energy level first. And remember we said that the lowest energy levels were closest to the nucleus, that was energy level 1, and as you work your way up, they become higher in energy. So what you have over here is you have an arrangement of energy levels, and these little boxes are kind of like the apartment buildings, or the apartments and the rooms in the apartments that I was showing you. Notice that all of the S's have one box because the S only has one orbital, and all of the P's have three because the P's have three orbitals, so therefore there's three boxes, one for each orbital. The D's have five and the F's have seven. This isn't complete. There is a 5F, like there is more than this. However, it just goes up through 7S. And what this is showing you is like the lowest energy is down here, which is 1S. So that means we have to occupy 1S first, and then we can fill the 2S. So you have to go in order. You can't just skip around. Okay, the reason that they overlap like this is because the two P's, they have more energy than the two S's. And then the three S's have more energy than the two P's. Three P's or more. And next one up, if you held a ruler up here, you'd be able to see the four S's are next, then the three D's and the four P's. Which is kind of getting at this last statement, to skip ahead, which is that the arrangement of this does not follow a simple pattern beyond the second energy level, which is right here. If you just wrote these down, you would probably expect that everything that's in the 1 would be all together, and everything that's in the 2 would be all together, and everything in the third energy level would be all together. And if you look at this, you can see the fourth is spread out. Here's 4S, 4P, 4D, 4F. In between that is 3s and 5s, and like, it's kind of crazy. It really is. It's all over the place. The good news is you don't have to memorize this. I will show you a trick for how to do it. Okay. Another thing of this says, of the Offball principle, says that orbitals of any sublevel of a principal energy level are of equal energy. So what exactly does that mean? What that means is that, like, take 3D, for example, right here. 3D is one of the sublevels, sublevel D. All of the orbitals in this part of the D, in this little section right here, they all have an equal amount of energy. So none of these 5 little blocks, 5 rooms, 5 orbitals, none of those has any more energy than the other. They are all equal. Okay, now take the 4D up here, and I can even switch colors just to make it stand out. The 4D up here, okay, 4D also has 5 of the little boxes to fill. all 5 of these boxes are equal in energy to each other. Now, the 4D as a whole has more energy than the 3s, but all of them within the same sublevel are of equal energy to one another. Okay, hopefully that makes a little bit more sense. We do need to know that, like, within the 4D, that all of these are equal to each other, because Offball says you have to put them in the lowest energy first. So if one of these had less energy than another, we would need to know it. But what this means is it's fair game. They could go in any of them in the 4D at the same exact time. What we need to work on next is, how do we know? Like, how do we start putting electrons in these, and what do we do with all of this information? This may be a video. It's going to be a longer video. I can promise you that, just because it's going to take more explanation, and it may be one that you want to watch a couple of times. So, what is an electron configuration? Right here is an example of one. How do we interpret it? What is it? What I tell you in words up here is that this big number, it tells us the energy level. Okay? Then you already are familiar, or should be familiar, with the S, the P, the D, and the F, and what those stand for. Sometimes this doesn't want to let me change colors. I have this problem in class. I'm not sure what it still is. The letters right there, those tell us which sublevel. And then last but not least, eventually I'll give up switching colors. Last but not least, these little numbers, the superscript numbers. This tells us the number of electrons. So what does this whole configuration mean to me? It means that sodium has 2 electrons in the S sublevel of the first energy level. It has 2 electrons in the S sublevel of the second energy level. It has 6 electrons in the P sublevel of the second energy level, and it has 1 electron in the S sublevel of the third energy level. It is a way of telling me where the electrons are located in sodium. Okay, some things that you could interpret from this. If I ask you how many energy levels did sodium have electrons in, you should be able to look at this and then just find the biggest of the big numbers, 3. Well, it's got electrons in 3 energy levels. If I ask you how many electrons that this atom of sodium would have within it, maybe I'll clear off the page, maybe not. I give up. Oh, nope, shouldn't. If I ask you how many electrons are in an atom of sodium, then you just add up all of the little numbers. There's 2, 4, 10, and 11 to add them all up together. So sodium has 11 electrons. I'm able to figure that out by looking at those little superscript numbers. Okay. If I ask you what its highest filled energy level was, and it doesn't mean filled, just, not completely, but like the highest energy level that it has electrons in, then you find your biggest number, your furthest one out, and you would say 3. Its highest energy level that has electrons in it is 3. Okay. Now what we need to work on is how in the world are we going to be able to learn how to write these things. And it's actually not all that hard if I teach you some tricks. Telling you how might be a little bit more complicated. So here's the basic gist of this. I prefer the periodic table trick. You're going to have to do parts of this anyway. It just makes sense to me to go ahead and use the full trick. So on your periodic table, the first 2 columns, the first 2 groups are referred to as the S block, or the S filling block. Okay, what that means is that these are going to represent the S's. 1S, 2S, you can see 3S, 4S. How you remember the numbers is you just number the rows. So that literally you just count down on your reference table and see which row it's in. Okay. The middle section, we'll learn the name of this later, but this middle section in blue is referred to as the D block. These are D filling elements. Okay. The P block is over here to the right. It's the other tall group. There are 6 of them. It's referred to as the P block. Now, if you start looking at this for a second, you may be looking at the numbers and going, wait a minute. Okay, on your reference table, this is helium right here. Helium should belong with the S's over here. There is no 1P. If you remember from our previous things, we learned this about the energy levels. we learned that the first energy level had S, the second had S and P, the third had S, P, and D, the fourth, remember, had S, P, D, F, the fifth has S, P, D, F, the sixth has S, P, D, and the seventh would have S and P. So that being said, there is no 1P. This cannot be 1P. It has to be 1S. It's in the first row, so it's got to start with 1. It's not 1P, it's 1S. That's just something that you're going to have to know. Okay, this one starts with 2P because, well, that's the first place you have a P is in the second energy level. So this is row 2. We go straight across right here. It's still in row 2. 2P. Okay, if you look at the D's for just a second. This D area, I don't have a 1D or a 2D. And if you look up here at what we know, we don't have Ds anyway till we get to the third energy level. So what I do is I just remember that for all of the Ds, I have to take away 1 from the row. In other words, instead of this being 4D because it's in the fourth row, you see on the fourth row we have 4 S's and 4 P's. This isn't the 4Ds, it's 1 less, it's the 3Ds. The fifth row, the 5s, it would be 4D. The sixth row would be 5D, and the seventh row would be 6D. Okay, I know that this is a lot, and a lot of this will fall into place as we just keep going. All I can say is just have a little faith, rewatch it, and let me do some examples with it. The F block down here. Okay, the F block, they're the 4 Fs and the 5 Fs. And you can't exactly see it from this one. I'll show you another picture of a periodic table in a second that explains it a little bit. But the F block really and truly should fit in right about here on the periodic table. If we could cut the table apart right here, where I just drew the yellow line from top to bottom, if we could cut it apart, here I'll go ahead and show you, it would look like this. Right here is where I would have made my cut, okay? And we take the section that's right here at the bottom, and we move it up here, it would look like this. And the problem with this is that it would be crazy long, and it doesn't fit on sheets of paper. And so what they have done is they have taken this table for the sake of our sanity, and they have come in here and they've cut right there on the red line, and they have cut right here on this red line, and they have taken this whole red section that I'm circling, squaring, whatever I'm doing, and they have moved it down to the bottom into its own real estate, and then they have scooched these other two sections closer together, and boom, we're back at this. Now, look at it for a second. This says 4F. Well, where did it come from? Look over here. It came out of the 6th row. 6S. So instead of being 6F, we don't have a 6F. We need to take away 2 now. Instead of this being the 6F row, it's the 4F row. And instead of this being the 7 Fs right here, this is the 5 Fs, okay? So one of the things that you should at least be able to do by just, like, you should at least know the blocks. That is one thing that you have to know. It is required of you to know the blocks. So what can we do with this? If you look at a reference table such as this one, and I ask you what beryllium would end in with its electron configuration, if you know the blocks and you know that this right here is the S block and this is the second row, then what beryllium should end in is 2S, because this row right here that I'm covering up in red represents the 2 S's. I get that from here. Okay, if I ask you a question about something like, what would boron end in? Well, I'm still in the second row, because here's the first row, the second row, and I know that this is the P block over here, so it would end in 2P. All right, hopefully this is making sense to you. If I ask you what chromium right here would end in, well, then you would look at it and you would go, it's the 4th row, and it's the D block, but I know I have to take away 1. It's not 4D, it'll end in 3D. Chromium will end in something 3D. That'll be the final sublevel that it has, okay? So we're putting this together little pieces at a time. You know, I would definitely recommend knowing that this is the S block, the D, the P, and the F. All right. So what I want to do now is do some practice problems with this. Like let's write the whole configuration. And if you have no idea what I'm doing after the first time, it is totally okay. You will not be the first student in the history of chemistry classes to not understand what I'm doing. Just give me some time, and I think with enough examples, you will make it make sense. Okay. So I'm gonna do lithium first, right here. Right here's lithium. So the first electron configuration that I'm gonna write is lithium. So what we do, we always start at number 1. From what we've done already, you should be able to know at least that lithium will end in 2, and these two are the S's, so it'll end in 2S. But we need to do all of the rest of it. Like, you need to be able to give every single detail. So always start up here at the beginning with hydrogen and follow the atomic numbers. So if hydrogen is number 1 and lithium is number 3, then I need to work my way through every single element to get to lithium. So here's the deal. To get here, I'm going to go through both of the 1S's. Because remember, this is the S block right here. This was the D's, the P's, and the F's are down here. Okay, and remember this was an oddball out. It represents one of my S's. I have to go through 1 and 2 to get to number 3. So I am going to write down 1S2. I put the 2 there because I went through both of them to get there. The 2 represents the number of the 1S's that I went through. Then, if I go through 1 and 2 to get to lithium, then I represent where lithium is at by writing down the new row number. I'm in row 2. I'm in the S's, but I do not go through both of these blocks to get to lithium. I stop in the first block. So I write down 2S1 because that's where I stop. So lithium's electron configuration is 1S2, 2S1. I'm sure your mind is now blown. Let's try another one. Let's do boron. Boron is right here. Element number 5. Okay, same rule. Always start with hydrogen. Start there. Start with number 1 and go through everything. We are going to record the numbers and the letters of everything we go through. So if we start here, in order to get to number 5, we have to go through elements 1 and 2. Well, they represent the 1S's, so I will write down 1S. We went through both, so I write down 1S2. Okay, then that leads me here. If this is element number 2, I go to element number 3, which is right here. Why am I pointing out that we do this? Because, well, it's going to help us at some point. Right now it seems kind of stupid. So I'm in row 2. So I'm going to put down a big 2. All right. I'm going to go through both of the 2S's in order to get all the way over here. So I'm going to write down 2S2. But that stops right here. Beryllium ends in 2S2. That is not my ending point. So there's nothing right here. Number 4 goes to number 5, so we just skip on over here. We're still in row 2, but these are the P's, the 2 P's as a matter of fact. But I don't go all the way through them. I stop in the first column. So I write down 2P1. That is boron's electron configuration. 1S2, 2S2, 2P1. Okay, so I'm going to be a little bolder here. We're going to go for phosphorus next. Phosphorus is P. I don't know why I did the equal sign all of a sudden. I just felt like it. Phosphorus. Phosphorus is number 15. So we're going to have to go through 15 different blocks in order to get there. We start at hydrogen. You go through both of the S's, the 1S's to get there. So we write 1S2. We went through 2 of those. That leads us here. We're at number 2. What's next? Element number 3. Right here, lithium. We're going to go through 3 and 4 in order to get there. Those are the 2S's. We went through both of those, so we write 2S2. Okay, what comes after 4 is 5. So we will be able to go through all of these If you pay any attention to it, and look at this periodic table, that is not right. That should be a 10. They're wrong. Wherever I got this from, wherever that links, shame on them. We will go through 5, 6, 7, 8, 9, and 10 in order to get to 15. This represents the 2 P's. We are going through every single one of them. There are 6 of them. So we write down 2P6 because we went through all 6. After 10 comes element number 11 and 12. Well, now we're in the third row. These are the 3 S's. We go through both of them. So we write down 3S2. 12 goes to 13. And we're going to stop at 15. So we're going 13, 14, and 15. Well, where are we? We are in the 3 P's. But we do not go through all 6 of them. We only go through 3. So we write down 3P3. Hopefully, this is making sense. If it is not, then you need to be very sure that you get to me during office hours, or that you send me a question or you put it in the question and answer for this, because this is something that's pretty critical for a lot of things as we move forward. Okay, so as I'm doing this and you're going, I don't understand where you're getting those little numbers from, or I don't understand where you're getting those letters from. First of all, you can always go back in the video because we did explain it several slides ago. I'd recommend going back or send me the question. Now, let's go a little bit bolder here, and let's do something that's going to go into the D's. So let's do titanium. Titanium is number 22. Okay. Again, y'all, we start at number 1. We go through both of the 1S's in order to get here. So that's 1S2. From here, we go to the 2S's. So we go through both of those. So that is 2S2. Then from there, we are going to go to the 2 P's. I'm following my atomic numbers here. We're going through all of those. So we're going to write down 2P6. All right, that leads us to 10. 10 goes to 11 and 12. Those are the 3 S's. We go through both, so we put 3S2. Then 12 leads to 13. Well, to get down here, we got to go through all of the 3 P's. So we're going to put down 3P6. Okay. Then that's at 18. That's where it gets us right now. 19 and 20 are right here. We're now in the 4th row. Those are the S's, so that is 4S2. Now we're stopping right here on 22. Well, where are we at? The 40s. No, wait. Remember, you're just, I don't have any other way for you to do it. You're going to have to memorize that you take away 1. It's the 4th row, but this is going to be the 3Ds. And how many columns do we go? 1, 2. So we write down 3D2. Okay. So there we have it. We have titanium's electron configuration. And it is going to keep working exactly like this all the way through the table. Now, when we get to the F's, I have a little bit of explaining that needs to be done down there just because of the way some periodic tables are done. This table that I chose, excuse me, is done like your reference table that you will be using for the NC final exam. And you need to be using your reference table to do these. You do not need to be using another reference table that you have found online and printed off. I really want you using the North Carolina reference table because that's the only one you're getting at exam time. When we get down here to the F's, small problem here with the numbering of stuff. And again, I didn't make this. I am the messenger here for it. I know students always hate this, but it goes 55, 56, 57, 72. Like that doesn't make any sense. Well, let's go back a slide. Look at this one. This one has them together as they should be. And if you look at the symbols here, you have LA and then CE. LA and AC right here are the first 2 elements of the F's. Okay, well, look at yours. LA and AC, well, they're up here. They really should go down here. LA should really be the first box right there. And AC should really be the first box on that row. So would that leave a hole there? Would there just be nothing? Nope. Go back. Look who's hiding right there. LU and LR. I've written all over it so much you really can't see, but it's LU and LR. Well, they're right here. So these two, they should really take a little trip, and they should really journey up here, and they should really be sitting in these spots. So that should be LU and LR. Now, in a perfect world, we wouldn't have to be doing this little mental shift-a-room. And maybe you're even asking yourself, why does it even matter? Well, because if you're not careful, you are going to botch your electron configuration, and you're going to split up the 4 Fs and the 5 Fs. And you're going to go like a D, the Fs, back up to the Ds, and it doesn't work that way. So let's just see how this would work whenever we do this. There's got to be some trick to this. Let's just do something down there and see what this would end up like, okay? So I'm going to show you how it would have to work on a test type situation. So there we go. Well, I managed to erase. And I would just go on, but I have no Oh, Malanta, pick the stupid pen. Okay. Okay, I got to thinking about it, and I decided, you know what? I'm just going to keep going with this video. Hopefully, though, you still can pause it and you can stop and do some of these configurations. I'm not over 30 minutes yet, so I'm just going to keep going. I know I'll be there soon. There is another way to do this. I don't think I've ever had a student who has chosen to do it this way, but if that periodic table thing is just driving you crazy, then look at this, and you may decide that the table thing is worth understanding after I show you this. There is another thing called the diagonal rule trick, and I can post some YouTube videos with this too, where you actually have to do math in order to do how you do your electron configurations. Actually, let's just do that. I will post a link for an alternate way, and that will just save this video from being even longer. So we'll just put in here, see YouTube link. It requires you to keep track of your electrons. So for example, if you have an atom with like 92 electrons, you're going to have to place 2 of them, subtract it. Then you're going to have to know that you have 90 left. And you actually have to do quite a bit of math to do it. The trick is much simpler. This also doesn't allow you to do noble gas configurations or the shortened configurations. So not my favorite thing. Okay, we already went through this. So let's look. There are some exceptions to Offball. We just worked with Offball to do this. Actually, I think I read somewhere that Offball works about maybe like 60 to 70% of the time. I am more concerned with you being able to do the general rules and not a bunch of exceptions to things. So I do want you to understand, though, how this works, and it is basically called electron promotion. We're going to do 2 examples here, and I don't mean that to be C. I think I meant it to be CR. I'll look at it in just a second. We're going to work with copper and chromium. I'm going to go back to this slide with our periodic table, and I'm actually going to clean everything off of it, and we are going to look at how there are some exceptions. So yes, I meant to do chromium. So if we look at copper and chromium, here is what you would expect for copper. For copper, we'll do the shortened version. Argon is the previous noble gas, so we would expect it to be AR in brackets, and then we would expect it to be right here. We've got row 1, 2, 3, 4, 4s2, and then it would be the 9th one over, so that would be 3d9. Chromium we would expect it's in the same row. We would expect it to be the same way. We would expect it to have argon first, 4s2, but then it would be 3d4. So this is not correct. And so what it said over here, if I go back, is that some of these are more stable if they have like a half-filled sublevel. Well, half of 10 is 5, and this is really close to 5. And if this one had just one more, it would have a full sublevel. And since this is called electron promotion, maybe you're able to figure it out ahead of what I'm going to do. But what it does is it robs 1 from the 4s, changing that to a 1 and this to a 10. It promotes an electron, hence the electron promotion thing. You get it? So it promotes 1 from the 4s up to the 3d. This one does the same thing. It turns this into 3d1, and 4s1, and this into 3d5. I can't speak anymore. It promotes 1 up. So how do you know how to do this? Well, basically, the d4s and the d9s. If you can remember that, then you would have a pretty good prediction. So you could predict that molybdenum, this is MO, would do electron promotion. So instead of ending in 5s2 it would probably end in 5s1 Same thing goes for silver. It would probably end in 5s1 and then 4d10 instead of doing it with the s2d9 like you would otherwise expect. If, on the whole, this is not my greatest concern. My greatest concern is to be able to do what was in red in the first place, and it's extra points for you if you can remember the electron promotion part of it. Now, the last piece. Okay, this is easy. This is really easy. If you get all of this electron stuff, then you will get this, okay? So there are these things called off-ball diagrams, orbital notation, orbital diagrams. I've heard them called like many different things, and they can look many different ways. Sometimes they're boxes like this. Sometimes these are done with circles. But what you do is you are going to fill these in based on the electron configurations, and you are going to use arrows. So for example, if we were going to do the electron configuration of boron, and I'm choosing it because I know what it is off the top of my head, which is 1s2, 2s2, 2p1, then what you would do is you would draw arrows in each of these boxes representing the electrons. We typically draw an up arrow and a down arrow. Now, the reason that we do this is because it represents the spin of the electrons, and they spin in different ways. So how this has to go in is you cannot have 2 up arrows in the same boxes. Likewise, you cannot have 2 down arrows. Both of those are no-nos. And this is really small for me to do this with, but you'd have an up and a down. There's 2, right, in the S's. So do 1 up, 1 down. There's another 2 in the 2 S's. And then in the P's, there's only 1. I just usually start at the left, and I do ups first. I don't really know why, if that's a rule or if I just chose it somewhere along the way. Okay, if we move on across the periodic table, this is boron right here. Our next one over would be carbon. Okay, carbon ends in 2p2. So what if this was carbons? What would we do with it and we were going to turn it into that? Well, here's the thing. Another rule for this says that you have to put as many electrons as you possibly can spinning in the same way. What that means for us is if I can have 2 up arrows, I'll take that instead of 1. Or if I could have 3 up arrows, I'd rather have 3 ups than just 1. Well, the only way to do that is to put it in its own box. It won't share rooms. And kind of how I tell my students to think about this is it's kind of like having roommates, since I've compared this to an apartment. If you could have your own room, most people would do that before they would share. So the electrons, they just like to have their own room before they're going to group up with somebody else. So don't you dare put them together until you have to. Do not fill up a box until you have at least 1 electron in every other box. So what if we moved on from there to nitrogen, which has 3? because it'll be 1s2, 2s2, 2p3. Well, then we would put a third one here. Who's next? Let's see. I believe we're up to oxygen. I don't have a periodic table, so I'm doing this based on memory and praying I don't screw anything up. Well, oxygen has 4. So what do I do now? Every room is full. I have permission now to go back and double them up. I have no choice. They cannot go on to another energy level until I have filled up the one before, or the sub-level before. Okay, so oxygen is there. Fluorine is next. Fluorine ends in 2p5. So, well, then you're going to have to double up another room. And then after that is neon, which ends in 2p6. So, well, then you'd fill up the last room. You can do this for any of the elements. As long as you know the electron configuration, then you know where to fill these in. You fill them in according to the configuration. Some of my practice problems look like this, and some of my practice problems are like this, where they're labeled like 1s, 2s, and then I've got, it's labeled like 2p, then you've got the 3s, and, it's blanks. You do the same thing. You would just put up, down, and when I get to going really fast with this, I just kind of do like part of one, like up, down, that can go pretty quick. It's ugly, but it works, okay? So now, I didn't need that extra one. Now it is truly practice time. I am so sorry that this is like probably one of the longest videos we will have all year long, I hope. But hopefully all of the example problems helped you with this. If you have questions, please contact me.